Hi, everyone. My name is John Gilmore, as I'm sure Eric introduced. And today I want to present some work I've been doing over at Optimax Systems in Ontario, New York, using Simio to reduce agnostic part takt time in Simio. So before I get started with any of the nitty-gritty details, I just wanted to briefly go over with you who exactly Optimax is and what we do so that you can get a better understanding of the problem description that we're trying to solve. Our customers come to us typically for one of three reasons. We are excellent in all three of these areas of speed, precision and quality, and production reliability, i.e. delivering on time. Speed is our bread and butter. 30 years ago, Optimax started in a small barn in Ontario, New York, with the sole purpose of producing precision custom optics in a week. Since then, we still adhere to our 1-week commitment, but we provide excellent precision optical components to so many more areas than just prototyping. We also produce highly engineered solutions to areas like spaceflight, semiconductor deep UV lithography systems, and high energy laser systems, just to name a few, and so much more. So again, just before getting into the exact product description, I wanted to give you an idea of both just how difficult some of these parts can be to manufacture and what our more typical workflow consists of. Optimax is a very unique structure, even compared to other optics shops in the area and in the industry. We don't have just one overarching manufacturing group divided into departments like grinding, polishing, and testing, like most other manufacturing facilities do, but rather our manufacturing group is organized into 3 segregated groups, or cells that we call them, that are designed with the tools, people, and processes purposefully built for what they do. So we have 4 areas or cells in our facility that we use. We have prototyping, which is our legacy, prototype optics in a week. We have production, which is essentially consists of high volume orders that have been engineered from prototyping. They don't always come from there, but occasionally they do. Often they do. And lastly, there's LGO, which consists of large, high precision, most challenging, very special applications. Throughout most of the facility, we typically run orders that are very high mix with low volume. Even our production sector typically doesn't have many bulk orders that last more than several months, a year at most maybe. That is, until now. We've recently been approached by a customer that needed help designing a process for a particular class of optic. I don't want to give away too much, but this particular species of optic, especially with the size and quality they want, could typically take months up to a year for us to produce very few of these optics. Our customer approached us asking if we could decrease our takt time by over 600%. But there's a few catches that made this particular simulation project incredibly complicated. Firstly, before going further, I just wanted to define takt time here. It's not necessarily the same as lead time, which incorporates the time between part is ordered to part is received. Takt time is defined here as the amount of time between when we start doing something on the surface of the substrate to when that optic is complete to the specification the customer wants. It doesn't include things like material acquisition, time at the beginning of the system, QA, packaging, shipping, etc. In just takt time, the estimate for the quality and size of the part our customer wanted was extremely long. And as I mentioned, the goal for this project was to decrease this time by over 600%. I haven't even mentioned really the hardest part about this whole project. We don't even know what we're designing a process for. At its core, our customer wanted us to design the simulation, not to simulate a direct replica of the real world, i.e. a digital twin, but rather use Simio to design the process itself. We know general specifications, general size, general weight, a list of substrates it could possibly be made out of, but we needed to use Simio to implement controls of an agnostic process, something that is totally oblivious to what the part is itself and what the process is itself. So in typical manufacturing, most of the time, The primary goal is to manufacture a part that has the same dimensions that are provided by a customer. That's often the case with an optic or optical assembly as well, but in this case it was dramatically different. We needed to design a system where all of these parameters that are innate to any part of this, to any part that we normally make at Optimax without actually knowing what we're making. So in order to do these things, we needed to consider tackling three particular subtopics: the agnostic part itself and how that's handled, the agnostic process and how that's created, and most importantly and uniquely, the agnostic flow, how a part is going to go through a system. By part specs here, I mean mechanical / physical specs like diameter, weight, material, packaging, etc. And by final specs, I mean optical performance / measured specifications, which is often given as sort of image quality or surface details, both of which are complete unknowns to us. We don't know what the part is supposed to look like, what it's supposed to be made out of, or how good it's supposed to be. So not only do we not know what it's physically made out of, we don't even know how good it needs to be. Our customer essentially said to us, can you make us a simulation in order to define what the parameters will be for a minimized takt time without totally blowing the optical quality out of the water? So minimize takt time, minimize the bottom line, and not sacrifice too much of the optical quality, but essentially find out how much of that optical quality we can sacrifice to lead to a lot smaller values of the other two. I just wanted to put this slide in here just a little bit, just so you can see how complex some of the shapes are that we're actually manufacturing. The challenge of precision optical manufacturing is marrying the physical specs with the optical performance specs. It's more than just making sure the part is the correct shape. We always need to keep in mind that the parts that we make will undoubtedly be just a single part to a larger system. We need to make sure that through measurement processes like metrology, that we not only meet physical specifications, but also meet these performance specs so that our part isn't the hindrance to the system. It's often said in our industry that there's no bother making the part if it's impossible to quantify the quality of the surface. You could have the best optical surface in the world, but if you don't have anything that can measure and verify it, what good is it? Some of the final specifications for the surfaces we make can be so minute that they go down to the sub-nanometer level. If you don't have a machine that can measure past that resolution, then how can you even be sure that the part you're manufacturing and the process that you're using is a good one? Large-scale projects like this not only have typical capital expenses in machines to manufacture the part, which can cost over $1 million in their own, but the measurement machines needed for such high precision can also cost equal to or greater than that amount. It can be scary making such an investment into a piece of equipment that, to the bottom line, has no value added to the part itself, but is unequivocally necessary to the process. This costing analysis that we wanted to perform is a feature inside Simio that made Simio an easier choice for the daunting challenge ahead of us. Getting down to such high precision makes the performance of the manufacturing machines themselves fairly variable. When even slight micrometer misalignments can cause unexpected errors, it makes it difficult to predict with absolute certainty what exactly a run through a specific process can do to your part at the output product. Even something as small as temperature can have a huge impact, some of these processes being significantly more variable than others. This stochastic nature of the processes themselves is also a reason we decided to go Simio. We're trying to find a way to predict and balance the variabilities we know how to control, all while trying to have two final goals here, right? Lower cost and lower takt time. Most of our processes do largely the same thing, but affect particular performance specs in different manners and take different amounts of time. We wanted to be able to experiment with these possibilities that certain steps themselves in our processes can be skipped altogether by taken over by other steps further down the process line because we got to a closer spec, a tighter spec earlier on in the process line. In essence, shifting the bottleneck between machines of varying precision. Through table structure in Simio, we're allowed to do this pretty easily. So We've decided to use Simio because it allows us to model the interaction between the requirements of physical specifications, optical specifications, process variability, and discrete flow adjustment. Simio's discrete event handling allows us to do all of this. All right, so now I just wanted to show you exactly what our process flow looks like. So I don't want to go into too much detail and blow your minds here, but this is an overarching view. I'll zoom in here in a second of the entire flow of our system. You'll see that we have this kind of lighter area here, which represents a sort of subsystem where we don't want a specific amount of parts to be in that subsystem at once. And the sort of queuing logic that we use there is a little bit different once parts actually enter it, as opposed to parts being outside of it. So you can see here that we have these checks and balances here. We have a check at each step in the process to say, are you good enough to continue? And we also have these flows here where, say you get to this spot right here, then it is a possibility that after this check, after this process, you are so good that you come over here, go here, and then you're still really good. And then you come over here and just totally exit the sub process in general. It's a very rare case, but it could happen. So we implemented the real world situation into our model. The more likely case, which happens more often than I like to admit, is that we go through this sub process here and end up getting to this check at the very end of the sub process, where we find that where one particular part of our part isn't as good as we'd like it to be. So we have to send it way back to the beginning of the sub process, close to the beginning of the sub process, in order to go through the entire thing again. So each of these processes, these sort of cycles here, target two things in particular. I don't want to give away exactly what they target, but we'll call them error species 1 and error species 2. So those are the two things that we're trying to reduce here to get a good quality part at the end. The tricky part is that most of these processes, in fact, the first, second, third, and fourth, and sixth, all reduce the first type of error while increasing the second one. And then you can probably guess what this fifth step does is it reduces the second one while increasing the first one. So it's sort of a balancing act here, right? Is that you want to get obviously the lowest amount of error in total possible, but how much error can you pass on to a next process such that you don't induce so much of a different one in other places? All right, so I'll zoom in here now and kind of show you a little too close some of the actual details. All right, so I'll describe this kind of blue section up here in a little bit. So we have our first process, pretty straightforward. We enter the process, do the processing, either pass or fail the initial metrology check. If we pass, and it actually can't fail at the first one. So when we pass, we go into the second one, processing. Yeah, we enter it, we process, we do a metrology check. And in this case, if we fail, we actually want to just totally scrap the part out of the system in total. But if we pass, then we continue on to the subsystem over here, where this is where we expect our bottleneck to be, where most of the parts will spend most of their time in this system, which is why we want to be so careful about how many parts we let into here. Definitely a good experimental variable that we'll use in the future. So in this process, we let a part enter. The first two steps sort of decrease the surface error 1, the surface species 1, while the third step in this sub process decreases the second one while increasing the first one. And so, as I mentioned before, you can kind of get stuck in this loop in here, and it can be sometimes quite difficult to exit out. Which also is another fair point, is that we have it set up that you can only go through a certain process a certain number of times before you're like, nope, we're going to scrap it out of the system. It's just gone through the process too many times. So in order to not have one problem child stuck in the system constantly taking up resource space and time, and just kick it out of the system when we feel like it's just a lost cause. And so then once we exit the system, we enter this final step in the process which this step is actually incredibly deterministic and will get rid of almost all of the error that's on the part. However, there's a trade-off that it takes an exceeding amount of time. So you could essentially just throw a part right into this final step in the process and say, get rid of all the error, make the best optic in the world, but it's going to take you about 2 years to make one. So, no thanks. Okay. And so now that I feel like I've pretty much described most of the process that we're trying to implement, few minutia here and there. So this part up here sort of describes how we want to be able to skip certain parts in the process. So there's 2 parameters really that the customer should be able to enter. They're not called this in real life, but I just wanted to sort of mask what they're called here. And I call them difficulty, which can be on a scale of 1 to 4, and part complexity, which can be either high, medium, or low. And based on how high both of those values are relative to each other, the processing time is either high, medium, or low. And so if you have a high processing time, then typically you spend a lot of time really getting the part to a really good optical quality, but then you sacrifice takt time, you sacrifice your bottom line, you increase both of those while decreasing the, increasing the quality of the surface, decreasing the error of the part. And so you can have these sort of different flows where based on the difficulty and part complexity, your process time varies. We take certain parts out of the entire process out, changing the flow of the part, and then that will start to sacrifice your optical quality a little bit. But if it's really takt time and the bottom line that you care about, this might be what you want to try and implement. All right. Done that. I want to go back to the PowerPoint and give a quick little introduction to what I'm going to show you in the model. Now that I fully described our process flow and the project that we're trying to implement, I wanted to demonstrate 4 key structures we have in Simio. Firstly, the animation which provides our customers a detailed representation of the cell in our facility that will, oh, that was weird. The cell in our facility that will manufacture these parts. It's prone to a little bit of physics breaking, so just a fair warning. Second, I wanted to demonstrate how we're able to visualize the results and possible changes we make to the part and process itself to see how we can make better throughput. Thirdly, I wanted to show you how we implemented some custom processes to implement some of the unique metrology and surface testing that we have. And lastly, but most importantly, is our table structure, which adds a level of robustness that's simply not possible in any other modeling platform. All right, so without further ado, let's head on over to Simio. Oh, that's not what I want to do. You come here. All right. So the first thing that I just want to show to you is just a little bit of the actual 3D animation that we got going on here. That's not the right button. So you can see that the parts come in and then they wait inside of the machine while they're being processed. And a lot of the processing times in this are quite large. So it's pretty difficult to really see flow through the system unless you really speed it up. And these parts are going to start going like really fast. So yeah, you can see there's another part in there now, and they're kind of moving them around the system. We can increase this even a little bit more. Part's really going to start moving. All right. And now I have this other model set up over here that has a little bit less detail in the 3D animation, but a little bit more detail so you can really see what's going on between the transfer steps in the process. So you can see that you initially enter parameters over here. We have difficulty and complexity, which will kind of dictate which parts of the process we either keep or remove. And just as an initial test, you can see that the parts kind of flow through the system. Going on their merry way. We'll fast forward. You can see the results. Bam. And so you can see that over time, this is over a 3-year period, we get simulated about 46 parts out. And these numbers don't really mean anything. the parameters I have running here don't mean much. Okay. So over to our processing logic, we can see here that we have a lot of unique custom processes that we've defined here to dictate how parts flow through the system, the logic of what happens when a part fails, when a part doesn't fail, when a part can even fail in its own right. We have a custom model entity, a custom server, which allows us to dictate how each server interacts with each model entity and how each error species kind of reduces or increases on the server side. So you can see here, in particular this one, the metrology failure check was quite undertaking in order to smooth out all of the process steps that really needed to be done. And probably one of the biggest notes is that when the simulation starts, those two parameters, the difficulty and complexity, will really dictate a lot of what happens in the rest of the process. So I'll show you some of the data tables we have. So we have error species 1, and then there's error species 2, and, or sorry, these are complexity and difficulty, which help change where your breakout basically leads you. We call these breakout tables, and it leads you to a different part in the process based on what your two inputs are. And you can see that we have basically our entire system set up as a table structure. We have our processing, or well, I guess these are the error species, how they get removed from the part, depending on which process you're going through. And then this is also the error species 2, how that changes depending on which process you go through. And then we also have how the actual processing time is handled here. With each step in the process, different things can change after the actual step is completed. So we decrease the amount of one particular type of error on the part during different parts in the step. And these are our equations for processing time, which are based on the machines that we have down on our shop floor. And so, yeah, that's in essence the biggest part about what we implemented here is the data and table driven structure. That's really the core behind the simulation that we've built up here. All right, so now I'm going to go back over to the PowerPoint. All right, and just to wrap up here, I just wanted to outline some of the biggest challenges we encountered while attempting to simulate our floor in order to design the agnostic process. Simio has many features, so the learning curve from novice to master modeler is a little longer, depending on the individual's background and skill set. Fortunately, Simio offers hypercare with expert modelers who can assist new users. Shout out to Ryan Luttrell. We found that to be extremely helpful, both for learning and meeting project deliverables, so I would highly recommend hypercare. Some of the training materials are a bit behind current software with respect to some interface elements that are currently in the software, but don't have a lot of good training material. I can't recommend enough the LS series of training videos, but some of the documentation in Simio itself can be a little bit confusing to novice learners. Some of the tool tips and documentation can be a little cryptic, but resolves with some more time spent learning the features and mechanics. Overall, though, because of how robust Simio is, I cannot recommend it enough. There's still a little bit of room to grow, and I can't wait to see where the platform comes next. So with that, I want to thank you all for coming to my talk. And does anyone have any questions?
All right, thanks, John, for the great presentation. I know it can be difficult to go through that much detail when it's blinded, so I just want to say that was great presentation, and of course I appreciate the shout out as well. So just to get started with some of the questions we have, you know, can you elaborate a little bit on how you were able to create the process flow without, you know, the part or the process actually being, you know, actually existing or being anything you're doing today?
So I suppose a lot of the shapes and materials that we frequently see through our shop are pretty standard. So we have a lot of people with a lot of experience that can have a good gut feeling as to saying, yeah, I mean, this will probably take about this long, and this particular machine will do this to this type of part. So I'd say, yeah, it's mostly just relying on the experience of others to be able to get the sort of data, as you will. Eventually, hopefully, we'll be able to get actual physical data over time as we run more parts through our system and have more structured ways to get data and run some demonstrations through our system. But until then, it's pretty much just people with experience.
Just a lot of tribal knowledge, huh?
Yeah.
Yeah. Great. Okay. Yeah. Thanks for that. So another question we have is on the animation. The animation looks great. What were some of the more difficult things to animate, if any?
So definitely one of the most difficult things to animate, which Ryan, you can probably attest to too, is we're still in the middle of trying to animate this new object that uses a worker as a driver to move the parts around the facility. Getting the network set up for that so there's not some interesting collisions that happen, and debugging it has been a bit of a challenge, and it's still not fully there yet. So I would definitely say that's probably been the hardest aspect.
Sure. Okay. So this one's talking about more how you've used the model so far. So have you all conducted any, experiments using this model? And if so, can you explain some of, the KPIs that you're using within the experiment to compare the different scenarios?
Fortunately, I'd say we actually kind of just got there pretty recently to be able to start running some experiments now that we know a little bit more information with some stuff that we've been running recently. So we haven't done anything just yet, but I'd say honestly within like the next week, we'll be able to run some pretty interesting experiments. And so since we haven't run any experiments yet, I can't exactly identify any particular KPIs, but we definitely think certain aspects of one particular machine will just like its speed rates and feed rates and stuff like that will be very identifiable. The particular material that the optic will be made out of, and that little sub process that I outlined, how many parts we let into there compared to how many parts we let into the system in general, we expect will be a very detailed KPI. Yeah.
Great. Okay. Well, sadly, that's all the time we have for questions here. But again, thanks, John, for the great presentation, and thanks for being a part of Simio Sync.
Yeah, thanks, Ryan.
Thanks.
This concludes this presentation. Please click on the back button to access the next presentation.